live. Yeah, it is now live. What do we have? Good. Good. So we are live. So the thing we need is the now work on your magics. Work on the logo and everything. Put them the way you want. So hata saa hizi tunaweza toa tu kamera. Sasa hii ndio sawa.
Okay.
Camera. But this one now will be like what we are live.
Okay.
Yeah. So we handle the signal there.
Yeah, tatu. Ukirudi itaipata.
So link kwa YouTube. Hiyo link ni gani?
Turudi YouTube, okay.
Get it, alafu share it with me. You already put the live, the banner.
Okay.
Yes, so we just want to give you the
Thanks.
unikopia hiyo link kama unaget hiyo link ya YouTube. Nini ukiteremka chini
Live. Tunaingia kaka. Share. Copy.
Use it on your phone.
Okay, yeah.
Just do this. Minimize. You don't need to miss
We're going back.
to go up. Yes.
Bado tunapewa the names.
Yeah?
Tunapewa the names bado.
The name ni vile tu vile wameweka ni sawa.
Okay.
You're good?
Music. Nitakomesha kuimba.
Any bit tu yenye kukula, sio kukula pale. Kukula. Sisi try, sisi kama. Choose any that you feel is
Business corporate.
nimekubebea hii. Do you have the earphones? Na inatoa sauti huko? Yes.
Uko on? Uko on? Oh, ushaka. Inachoma. Yeah, better. Busca, hakuna.
Kwa live stream ama
Kwa stream, kwa live stream.
kwa YouTube. Get sound wapi? So, enda kwa YouTube. There is no sound.
Comment.
No?
But still like big. Sisikia anything. Yeah, imeanza kukuja. Na iko sawa. Yeah, watu wawili.
Is that one? Now? I don't know if this one or this one.
Do we need to record ama iache? Okay. So zooming.
Yeah, you will start to
But I go on. How many?
no, still waiting for them.
Okay.
Make sure everything is not moving. When it's moving or running short, your cue. So that I'm cutting it. So it should be fast. Cue her, put, change them. Move from forward.
Data zoom.
slide is saying is if you have such a catch-all pattern that matches anything, must always be the last one. Because if I check the order here, and reload and try again, then we get two in both cases. Because the same line is never reached, right? Because the first pattern that starts at the top, tries one equation after the other until it finds a pattern that matches, and this underscore makes no meaning. So the order is taken first equation and never taken the second. So else, all cases must come last. And it's a best practice or useful to have to implement a function that operates on some complicated time or less complicated time. We split it into smaller problems where we will find case for each constructor and for any possible constructor for the private experiment. If the cases are not overlapping, the order doesn't matter. It may matter for efficiency, but the result is. And in this example, it was overlapping because the argument is true, no man's by the word pattern by underscore because the underscore matches everything, and by the pattern if the one of the equations, no matter what the value of the variable is in one of the equations, one of the patterns can be met, and it doesn't matter. One way to do this is to start with this equals to type rule, so that the relativity rule is let's say we do this again, and how to implement it. One important thing to do is we just start like this. So this underscore on the left hand side, you have seen that's the catch-all pattern, the pattern that matches everything. On the right hand side, basically, I mean, it's a hole. So it's an error, I mean, it's still compiled. But if you somehow, I mean, if there are pieces of your program that you don't know what to do with, then you can put this underscore in, and then the compiler will give you hints. So in this case, the compiler will say found a hole, and occupy who will do it. So I must fill this hole with something that is like it's not compiling because this case the rule is not defining, so type is not right. So that more information, so we see there's a hole. We see the where the hole is, we see the type. Now the situation has changed. Now there's still a rule, but now it's a different type, right? Because earlier I didn't have this x there, so it's still the whole function that I have right inside. But now I have to say not time of x, so this really is taken care of, and what I still have to define to say is in which medium this x is now x. Now the type of the rule is blue. And now I have extra information here, and in my context I have the x available of type 2. So this is again this pattern mentioned. So one of the possible patterns was variable, and so in this case, so I have the variable x. It matches everything, but then it also binds whatever the value is to this main x. So on the right hand side, I now have this x available to write or to so that is it already like tries to be helpful and gives me hints what I could possibly find. I mean, I could right kind of order. So I could, I mean, pick any of these three choices, and it would all make the error go away. This would be fine, or this would be fine, or this would be fine. However, it would be fine in the sense that the error goes away, but it's not what I want to do. Right. So what I can do now is follow this advice on the slide. This best practice advice, split programming by extending variables into all possible constructors for the type of variable. So let's try this now. So we have this variable x, and there are ways for x can be x equals 2 or x equals 4. So the advice now is to split this and consider those two cases exactly. Right. And now it's very easy to actually put now I have two holes, but the situation is clear because I know exactly what the left hand side is. And now I can just fill that in. So logical negation of 2 is false, and logical negation of 4 is true. I mean, I wrote that earlier. Right, but this is of course a very, very simple example, so I think it's very simple to see what's going on. So it's not very too much on that. So we did this, we split cases into possible cases for the two, and we solved it, so that was very easy. So everything looks good. Now let's try to triangle or margin. Right, let's try to, I mean, we saw that in action yesterday already, logical discussion. Now let's just define it, and I should just, I mean, here I call it not right. The problem is, I mean, this destruction is already built, so let's apply this. And the problem is that now I have to, if I try this, yeah, you can worry about that now. So the problem is that this logical disjunction that we saw, as we saw yesterday, is already in the prelude. And the prelude, as I explained yesterday, is always automatically imported. So there would be a name flash if I try to redefine it because it's already defined. But there's a way like this, what I now with the 9p, to hide imports. So now I hide the standard one and can define my own version of it. And I could have done that with maybe a shift not as well. And I wouldn't have had to call it not done. Right. So let's follow these steps again. So we want to implement that, we don't know what to do. And we now have the whole of this function. So the first step in the previous example was to introduce variables for all the function items. In this case, I have two arguments, so I can give them names, for example, x and y. So now I have a simpler whole, which is just of type 2, and I have two variables x and y. They're introduced on the left-hand side, bound by the left-hand side. Okay, but I still don't know what to write here. I mean, I'm seeing no explanation about what x and y actually is. So the next advice was to start splitting variables into possible cases with by the constructors. Now I have two variables, so I could split x or y or both, but let's just try with x. So I do what I did with not as well. So I introduce the second equation and consider the two possible cases for and now, actually, it's easier because I'm thinking, y, so I can make that clearer by replacing y with an underscore, which means that I can't use that anymore. Okay, what's in the second case? So because it's false, so the overall result now depends on the value of y. If y is true, the result is true. If y is false, the result is false. So I could, of course, now split on y to consider the case false true, false false. But in this case, I don't need to do that because I already know that the overall result is just y. So that was another example of this standard way of writing functions. Right, and as I already said, there would have been different choices. So, for example, I could have swapped the order. Here, I first considered the first equation in line 10 is x equals true, and the second was x is false. But the order doesn't matter. I could also have it done the other way around, false, true. Or, as I also said, if this is too much for me, I could have now split y into the two cases. So, I mean, I could have done, so we were at this point here, and then I could have created another equation and done it like this, and then it's like trivial to see what the results are. So that would also have been perfectly fine and correct, just a bit more verbose. Right. Or I could even have done, I mean, on the slide, so instead of doing this here in one go, two equations for that. But I think I don't do that now. Right, this is, let me just peek ahead quickly. Okay. Right. Let me just do this anyway. Let's write the second version. And I don't know, let's call it, I don't know, 3 bars. Where I do actually consider all 4 cases. So this will still have exactly the same results as the version I had before. If I import it first, sorry about this, now, right. Okay, and so Haskell can have errors. So you can have runtime errors. I mean, we talked about how wonderful the compiler is, that it catches lots of errors before you even run your program, but that doesn't mean that there can't be any errors. So it can crash at runtime. And one program that crashes is this one here. It's called loop. So let's just define that. So it's called loop because it's an infinite loop. So if it tries to evaluate loop, I mean, it matches the left-hand side, and the right-hand side is loop again. So it's relatively obviously an infinite loop. So you can see what it does if I try it in the REPL. And I mean, it just hangs. So I can now wait forever and it won't do anything. Okay, and then there's another thing, just hang on. Right. So that hangs.
now let's see what happens if I do true or loop. And if it was any other, no, maybe in this specific case not. So let's not. Okay, so I get the correct result true, even though we know that loop loops forever. But the point is, if we look at the definition, in the case the first argument is true, it doesn't even consider the second argument, and it is lazy. So as explained yesterday, in most languages, almost all other languages, when you have a function like this, in order to evaluate it, it would first evaluate the two arguments. So in this case, when it's trying to evaluate the loop, it would hang. But Haskell is lazy, so it only evaluates what it needs to evaluate. And because it sees the first argument here is true, it never looks at the second argument, and therefore it doesn't matter that that would hang, because it never gets to that point and immediately returns the right result. If, however, I do true with 3 bars loop, then it does hang. And the reason is that in this case, it must decide which of the 4 equations to try. And because I didn't use an underscore now, but like a concrete pattern, in order to know, I mean, the compiler or the runtime basically tries to go from first equation, second, third, fourth, and find the first one that fits, where the pattern matches. And in order to decide that, whether this equation match, I mean, okay, and it sees the first argument is true, so it will be this equation or that equation. But in order to decide which of the two to pick, it must see whether the second argument is true or false. And that means it has to evaluate the loop, and then it hangs. So that means even though the two versions of disjunction do the same on true and false, they give exactly the same results, they don't behave the same in all situations. So if one of the two arguments is like an infinite loop or an error, then they can behave differently. So it does matter how much you split. So as a general rule, one should try to like do as little pattern matching as possible. I mean, if you don't need the value of a variable, you shouldn't pattern match on it, because with each pattern match you decrease the laziness of the construct. Then there's also an asymmetry in here. I mean, I did the split on the first argument, but I could also have done it on the second argument. Then it would have been just as lazy, but in other situations. Now it was fine, I mean, the way it's defined, and also I think that's the same way it's defined in the prelude, if it's lazy in the second argument. Yeah. So if the first is true, it never looks at the second. But I could have written a version where it's the other way around, where if the second is true, it never looks at the first. That's just, I mean, historical, whatever, why it's like this and not the other way around. And this loop we saw.
You could also like avoid the second pattern match as well there.
This one here?
That could be like a variable that you just.
Yeah, that was the original version. That's the one in the prelude, I think. Yes. I mean, this is how it's defined in the prelude, I think. Yes, then it wouldn't need to look at, so then it would still be fine even if y is loop. But of course, if you want to evaluate it, I mean, if I type now, if I do it like this, it will hang anyway because it wants to show the result. But only at that point does it hang, not at the point where it evaluates this. Right. And we saw this loop which just hangs. So if you explicitly want to introduce an error into your code, I mean, typically you want to do that if you want to write that later, like a to-do. Then, I mean, you could use loop. By the way, this is also interesting. The type of loop is interesting. It's of any type. So loop has any type. And the reason is that because it hangs, it will never need to produce a result. So for Haskell, it means it has any type. And this is actually the only program that has any type. So you can't have a valid program, one that actually terminates, that has any type, because there's no value that's in every single type. But we get to that a bit later. But anyway, so you could, I mean, if you want to implement something, but you don't know how, so you want to put something there and then worry about it later. So you could use loop, because loop is of any type, so it would fit everywhere. But the problem is then if you run your program, it just hangs and you don't get any information. Therefore, there are like built-in things. One is called undefined, and that's also of any type, but that's built into the prelude. And so like morally it's the same. Undefined or loop is the same thing. It just hangs. But the difference is how it, what the runtime does with it. So if you type undefined instead of loop, then you get a nicer error. You get an exception, prelude, undefined, and also some stack trace information. So that's why that's better for this purpose. If you want to like leave some holes in your code that you want to fill later. And finally, there is something error that takes a string and produces an arbitrary type. And this is basically like undefined but with an error message. So you can do some, if you evaluate that, then you, also crashes like undefined, but instead of this generic error message prelude undefined, you get the string you provided. So you can give more information. This is typically used for real error cases. If there's something that should never happen, then you can give a proper error message. But we will also talk about error handling in Haskell later because of its lazy nature and the pureness. That's quite a tricky topic. Okay. At that. Right. Oh yeah, and just the last remark here. So I showed you this different behavior of the 2 vertical bars and the 3 vertical bars, so that how you like arrange your equations, how much you split that matters, can have an influence on performance or on behavior. And the last remark here on the slide is just that it's not only in error cases where it's an infinite loop, it's also for like very complex expressions that take a long time to evaluate. So maybe then it isn't an error, it wouldn't hang, but it would still take a long time. That's unnecessary because you don't need the value anyway. Right, next, another example on bool. And not sure whether I need to. Just 1 second. Right. So another useful function on booleans is if then else. So you have one boolean and 2 values of an arbitrary but equal type. And then the behavior should be that if this boolean is true, the result will be the second argument, the first A. And if the argument is false, then it should be the second A. So condition, if branch, else branch. And you could implement it like this. And in most programming languages, also standard ones that are not lazy, you have this behavior, short circuiting, I think it's called, that, yesterday I explained that most programming languages in a function, if you write a function like that in JavaScript, for example, and you evaluate it, then what I said yesterday is true, that it would first evaluate the Boolean and the first branch and the second branch, and only then evaluate the whole thing. So you would always do unnecessary work, because you only need that value or that value, but you never need both. But if you define this as in JavaScript, for example, it would always evaluate all 3. However, also in JavaScript, there is an if-then-else construct, and that does the right thing. So that doesn't evaluate both branches. First evaluates the condition, and then only the right branch. But that is a special built-in in JavaScript. And I just say JavaScript, but it's the same in almost every other language as well. So there's special behavior built into the language that enables that. So you can't, so that means in JavaScript, for example, you can't define your own if-then-else with this behavior. You can define this function, basically, but then it wouldn't behave like the built-in if-then-else. Whereas in Haskell, it does. It behaves exactly right. Because of the way this is defined here, we see in order to decide which equation to use, we only pattern match on the first argument, the condition, And we don't look at, I mean, here we don't pattern, I mean, we just use variables. So it means in order to decide which equation to use, it just has to evaluate the Boolean, not the two other arguments. And then it doesn't have to do anything with them, it knows the result without looking at it. And that, because of laziness, it means it never has to evaluate the T and the E. And I mean, yesterday there was a slide already where it said that in Haskell you can define your own control structure. So that's like this. So in Haskell, of course, we do have an if then else built in the syntax, but if we didn't have, we could just define it. I mean, it would syntactically maybe not so nice. It would be this function, but nevertheless it would work exactly like expected, not do any unnecessary work. So yeah, there is, but I showed that yesterday already, that there is a built-in if then else, so you don't need this function. We have a syntax construction in Haskell: if condition, then branch, else branch. But yeah, maybe one should just say that in many languages you don't need the else, so in Haskell you always need the else. Right, then there is another nice way to write the same thing. So maybe let me do it after all.
Why do you always need the else? You always have to return a value.
Yes.
It's like something not everyone thinks about, right?
Right. I mean, because in Haskell these things are expressions that have a value. I mean, in most languages it's like statements, they do things. So if a condition is true, you do something, and if it's not true, then you just don't do anything. But if then else in Haskell is an expression that has a value, for example, an int. So there must be an int in the end, whether the condition is true or not. So you must tell it what int to return in both cases. I mean, that's a bit like this triple, what's it called, ternary operator in JavaScript, for example.
Yeah.
So some other languages have that as well.
Functions always return some value.
Mm-hmm. Let me just write it, why not? Then else is...
I have another question.
Yes?
Maybe someone has, but don't want to ask. You said before, defining with the type of undefined, that you could not return a value of type A.
Yes.
Now you're returning a value of type A with the if then else.
Yeah, but I have one already.
Yes, that's the explanation that you want.
Oh, sorry.
So he can return a value of type A in the if then else because you have to provide the value as an input. So that's why he can produce a value of type A, because you are providing the actual type as input. In the case of undefined, you're not giving it anything, so there has no way of choosing a type, of giving your value because it doesn't know the type.
Yes, if I wanted to implement undefined without crashing, A can be anything. It can be int, it can be bool, but I don't know what it is. So there's no way for me to write down a value, I mean something that is of every possible type, except the crash. So Haskell, like there is one value that's in every type, and that's this crashing undefined. So I mean, if I have no information about the A, it's impossible for me to produce one. But in if then else, the situation is different because I have two A's as input. So I don't know what A is. It could be bool, it could be ternary tree, it could be anything, but I don't care because I mean I get one as input and all I have to do is pick one of the two as output. And there's also nothing else I can do. I mean there will be another lecture about that, but this is basically the only way I can possibly do because I have no info. I don't know what A is. So the only way I have to produce a result of type A, because I don't know anything about A's, so I don't know how to produce A's. So all I can do is pick one of the two that I was provided as input. So there are basically only 4 possible implementations of this function. Of course, only one is correct, but in order to have this type, there are only 4 ways to do it. I mean, I could, because I always have 2 choices. Do I pick the T or the E? this is also, I mean, as I said, there will be a lecture about that, but this is also very powerful, that often because Haskell is like highly polymorphic, or many functions are highly polymorphic, and these highly polymorphic functions often only have like one possible implementation or very few possible implementations. So it looks as if it should be harder to implement something for every type instead of just for ints or so, but actually it's easier, because the less you know about a type, the less options you have to produce someone, then that makes it easier to pick the right one. So even if you only ever need if then else for ints, it's still a good idea to define it in this polymorphic way, because then the implementation is easier. Right, so this is this first implementation, and we, of course, in this case we don't use the E, and in this case we don't use the T, so I should write it like this. And I mean, we can, of course, try it. For example, if C equals D, then Haskell else fourth, we get fourth, and if C less than or equal D, then we get Haskell. So and that was stupid, sorry. I mean, I wanted to demonstrate the function, of course. Okay, so this is how it works with if then else, and I should get the exact same behavior if I use the function I just defined, if I had imported it. Right. Right, so it behaves exactly as the built-in if then else. Okay, so the second way to write this would just be with the built-in, so condition TE if C then T else E. C, sorry. Right. And then there's another one that we haven't seen yet, and that's called guards. So so in these patterns, so there's a new syntax that we now learn that you haven't seen before. So we can, I mean, this is a normal pattern, so a normal left-hand side with 3 variables in this case. But one can have a condition that is checked at runtime. So and that is called a guard. The syntax is one has this vertical bar, and then you can write anything, any Boolean expression there. Right. So the third way to write that would be this. So that means in order to compute the value of the function, so in this equation, which is the only equation, so it's always that, in order to check which line to pick, I must evaluate the guards condition, and I start at the top. So I start at the top, find this guard, evaluate this condition, and if it's true, this is the definition I pick. If it's not true, I go to the next one. Otherwise, it's just because it sounds nice, but we can so if I reload and try again, I should still get the same that I got before. Yes, so it still works. If I just ask for type of otherwise, so otherwise is not a syntactic construct that's just defined in the standard library, it's just a Boolean. And if I ask what it is, it's just true. So otherwise it's just another name for true. And I mean, so you could just as well write true there instead of otherwise. It just reads nicer if you read the code, because then it's clear the intended meaning is. So you have like several conditions, and if none of them is true, then otherwise do this. And yeah, and which of these various options to pick is, I mean, a matter of experience and also a matter of personal preference. I mean, sometimes some options are better than others, but there's no clear rule. Okay, explain guards. Right, so this is Boolean. So we saw now a couple of examples, not logical disjunction, and if then else, how to define functions on Booleans. So now let's look at a somewhat more interesting type. I mean, Booleans are very boring because there are only two. I mean, the only more boring type is one we haven't seen yet that only has one possible value. And then there's one that has no possible value. But yeah, Booleans are relatively boring. So let's look at maybe next. And probably know that from other programming languages as well. But then it's sometimes it has a different name, like option or so.
Yeah.
So a maybe A is supposed to indicate it could be an A or not, or nothing. So it's an optional A. So we have two constructors. One is called nothing and one is called just A. So I could, for example, ask for the type of just C, and it's a maybe character. Right. So we have two constructors, nothing, which is of type maybe A for every A, and just, which takes an A and returns a maybe A. And functions on maybe will typically have this shape. I mean, as before, functions on Booleans typically have the shape that you have one equation for the false case and one equation for the true case. Similar functions on maybe, you typically will have two equations, one for the nothing case, one for the just case. Right. So as an example for a function on for a function on maybes, and this is actually also in the prelude. It's called from maybe. So it takes an A and a maybe A and returns an A, and the idea is if this maybe A is a just, then you just take that value, but if it's a nothing, you take the first argument. So this can be used, for example, for like default values. If you think you have some sort of function that has a bird attack.
Sorry.
It's fine.
Before you
Yes.
go further,
Yes.
does it make sense why there's a need for a maybe type? We just said that every function needs to return a value, but sometimes there's no value to be returned. If we try to divide by 0 or any, like we don't have anything that's actually worth returning. No, there's no sensible default value. So in those cases, you return the nothing to indicate that. And if there is, we return the value wrapped inside the just. That's why that's the use case for the maybe type.
Or at least the most common one, yes. And I mean, for example, just as an example for what you said, Robertino, with division, I mean, we haven't, I mentioned briefly yesterday there's a fractional type and that Haskell has doubles. So we could have my, my diff from double to maybe double. And my diff xy, now I can, for example, show you an example of how these guards would be used. So in the case that y is 0, it's nothing. And otherwise, it's just x divided by y. And so I could do my diff, I don't know, 24.8, and that gives just 3. But if I do my diff 24.0, it would do nothing. So that, I mean...
If he didn't do that, he tries to divide by 0, the program crashes.
Yes, if I just use this... it gives infinity, but...
Yeah. So this is just one of many cases where you can actually avoid a runtime crash by just making sure that all values that can produce this crash are handled separately.
Yes, that's something that's encouraged in Haskell. I mean, you can also have programs that crash, but that's normally not a good idea. There are like some historical problems that even in the prelude there are functions that do crash. but people are not happy about that.
Yeah. No, but there's also like, sometimes the problem doesn't happen often enough that it's worth the hassle of what Lars is going to do now, that is to pattern match and extract and then use it and then pattern match again, extract and use it. So sometimes it's so rare that it's just better to just take the chances so you can simplify your code.
Right, and this from maybe I always forget whether it's actually in the prelude. No, it's not. So it's in data.maybe, so I could define it. So was it from maybe? Yeah. So it takes an A and a maybe A and produces an A. So in the case that we have a value, we just return that value. But in the case that we don't have a value, we take the provided default. So that's in, as I said, that's defined in the standard libraries, but not in the prelude. So, for example, yeah, we can just demonstrate it. Sorry about that. From maybe x just y would ignore this default value I give and just return the y. But if I don't have something there, then it takes the default value. And I mean, one use case might be that you have some sort of command line parameters, and some of them are optional, whatever, I don't know, font size. So you model that as a maybe, but you want, if the user doesn't provide an explicit font size, you want to use whatever, 12, then you could use, I mean, this from maybe, and I mean, you could say from maybe 12, and the user defined provided font size or whatever, if that is of type maybe int. And then if the user has provided something, that would take, but if it's nothing, then you would take this default. So that's like useful. Okay, that's just an example. This is also good. So sometimes you have, like, you want something and you have several ways to achieve it, but each of those ways might fail. And so if you have several ways, you can try one after the other after you find something that works. And that's this or else. So if you have one way to possibly produce an A and another one to possibly produce an A, then what you can do is, if the first way already works, you don't care about, you don't even try the second one, you just take the first one. But if the first one results in nothing, then you try the second one. So, yeah. That's actually an instance of monoid, this one. Yeah, so there's like lots of structure there. But that's something we could do. Of course, you could also do the opposite, that you try the second one first. So, yeah, I don't know a good example right now when that's useful. I mean, you have two ways. For example, if you're looking up, I mean, sometimes you have like a config file and command line parameters. And maybe the command line parameters override the config file. But you have an option, this font size again. Let's say there's an optional command line parameter for the font size, and it could optionally be in some JSON config file. Then you have like two maybe font sizes, and you might combine them with or else to pick one. I mean, if the user provided one of the two, then you get it. But if there's neither command line parameter nor config entry, then there's nothing you can do. As example. So this is also quite useful. Okay, so I'm not sure. I think I don't have to do this. I mean, it's all just the 4 cases. So if the first doesn't work, the second is taken. If the first works, the second is ignored. If the first, it doesn't matter whether it's there or not. And if both don't deliver nothing, then the overall result is also nothing. Right. And then you also can modify an optional value. So we saw this map on list yesterday, which given a function in the list of A's applies the function to every element in the list and produces a list of B's. We can do something similar to for maybe. So given a function from A to B and a maybe A, we can turn it into a maybe B. And what do we do? Well, if the argument is nothing, we have two choices. Either we produce a nothing or just B, just a B. But in order to produce just a B, we need a B from somewhere. But we have no B available anywhere. I mean, the f is a function from A to B, but we don't have an A, so there's no way to get a B. So the only choice we possibly have is to write nothing in this case. And that means also we can ignore the function. And in the second case, well, there we can produce a B. We don't have a B directly in context, but we do have an A in context and a function from A to B. So what we can do is we can write just FA. So we can take the A we now have, apply the given function to it to get a B and return a just B. Of course, we could also have returned nothing again, but then it would have been a boring function. And we can try that out. Let me import this data.car again from yesterday so that I have the to upper function. And now I can, for example, do map maybe to upper. Remember, that's the function that takes a character and converts it to its uppercase equivalent. So if I do that with nothing, why? Then it's nothing. But if I apply it to a just Q, then I get just capital Q. And of course, it doesn't need to have the same type. So I can also map maybe length. The only complication is that I have to say what type that is. Don't worry about that too much. I get nothing. But if I apply it to a just, I don't know, Kenya, then I get just 5. So the length of that string. I did have to tell it here what type that I'm considering strings, because the length, as we saw yesterday, doesn't just work for strings, it works for all sorts of things. And then the compiler would have been confused and not known what type I'm at. So that's why I gave this type annotation. But don't worry about that now. Just examples. Okay, another example. Let's say we have two ints or not. Is that? Yeah, sorry. And we want to add them. So in this case, we can add them if we have two values. So if we have a just x, a just y, we can return a just x plus y. But if one of the two is a nothing, then we can't produce a result. We can't add them because I'm missing one of the. So I would just, probably on the slides it's different. No, it's not. Good. So in all three other cases, it's just nothing. We can try this out. So we can say at maybe just 1, just 2 gives us just 3. But if one of the two arguments is nothing, we just get nothing. Okay. Right. And we can generalize this. So this was now specifically for the add function. Haskellers always try to generalize stuff. So and this was specific to addition and that both arguments are int. And then you can say, okay, but but we can generalize that. So we could have arguments of two different types, a and b, and it also doesn't have to be addition, it can be an arbitrary function taking two arguments. And I can have maybe a to maybe b, maybe c. And in cases like this, if it doesn't fit into a line, a lot of people, including myself, would then lay it out like this. As I said yesterday, you have a lot of creative freedom for laying out your functions. So let's first do the case where we do have an a and a b. Then I can do exactly the same as I did for addition. So I can apply my given function to the two values I now have. And in all other cases, when one of the two is nothing, I just return nothing. So this is just a generalization of this at maybe. We can try it out. Do we have a good, let's take one, like a binary function with two different types, lm for example. We saw lm yesterday, checking whether an element is an element in a list. So I could do lift maybe lm just y just Kenya. That returns just true. So I have the character, I have the string, so I can apply the lm function to check whether the character y is in the string Kenya, and the answer is true. But if one of the two arguments is nothing, for example the second one, then I just get, okay, and now I have the same problem that it doesn't know the type. Sorry. But yeah, then I get nothing. Right, so this is just a generalization because I can recover my original at int by just using plus for the function f. So what I tried before with just 1 and just 2, it works as before. So this is a generalization. Just checking whether there's another example for lift. Sorry, for maybe? No. So I think we should have a short break, 5 minutes or something, or 10 minutes. Except if there are questions. Yeah?
The maybe function and the boolean function, they kind of look similar.
Uh-huh. Yeah, I mean, they look, I mean, one reason they look similar is that they both have two constructors, so you always have two cases to consider. But this is exactly basically the goal of the lecture, to see why we always, why it's so boring. I mean, I was joking with my colleagues earlier, it's a horribly boring lecture because it's always the same. And I mean, the point of the lecture is to see that that's always the same principle. And then, of course, in Haskell we have ways, because we don't like work, or at least unnecessary work, duplicate work, to abstract most of that boilerplate stuff away and write these things very shortly. But yeah, very good question.
Yeah.
Other questions? Yes?
Is there a simpler way of, instead of being redundant, saying just x, just y, just x plus y, can you just maybe say just x, then maybe plus y, then you run to see the result?
Not completely sure what you mean, but there is indeed a, I mean, I would write, what?
He's asking if you could pattern match the just for all the values, just to get the values. So no, you cannot, because each value is its own maybe type. So you have to make sure that to pattern match each one of them, because you can have a single just and a not. You can have both just and one nothing. And if you try to pattern match just for all of them, you'll get an error. There's no just in the second value. But there's a way to extract all the just beforehand. But not sure if that's maybe another future lecture.
Yes, probably. But I mean, there would be a much nicer way to write this. So I would just, I mean, you could write that like so. So this lift maybe you could write like this. I mean, you obviously can't understand this now, but that's called applicative syntax or applicative style, and I like it very much. And so there are ways in Haskell to write these things very concisely.
So that's actually hiding what we are doing right now, like under the rock, and just use that. So if once you know those symbols, you can just read that and understand like perfectly what the function does, no matter the actual types that it's applied.
Mm-hmm.
It's really cool.
Yeah. Other questions?
We'll get into that.
Okay, then it's 42 now. Maybe start at 50 again, if that's okay? Or 10 minutes. Yeah, 10 minutes. Do we have to? Could you just switch me off, please? Keep it on, but non-valid comments, and then I said we also have blocked comments. So if I wanted to, instead of commenting out these two lines separately, I could do a block comment, and that's introduced with a curly brackets minus and ended with minus curly brackets. So that would be a block comment. So everything between the two curly brackets is a comment. And then we also have something, I mean, yes, we will see that much more later, something called Acted, where all the libraries live. And they, if you look at packets, they look very nice. I mean, some of them comments. So there's also a way that's also done in other languages, and also from C# for example, that you can do special comments that are then nicely displayed in documentation. There's a documentation for Cardano, but then you can do that later as well. Not sure whether there's a lecture for that yet. Okay, so this was maybe, so now we have blue, we have maybe. Now let's look at pairs. That's another, because pairs are so common in Haskell, that's another instance of special syntax. So pair, the type of pair of A and B, so you have an A and a B, is written like this. So it's in parentheses with a comma, separated with a comma. And the value of that type looks the same, also parentheses and comma. So for example, I could ask for the type of Q, true, and that would be of type pair of a character and a bool. So it will provide a character and a boolean, and then you get something of value pair character boolean. And actually in Haskell it doesn't just need to be 2, so we also have 3 and 4 and 5 and 6 and 7, and it stops somewhere, but I always forget where, but at 12 or so. But that's anyway bad practice to use these very long tuples. But you could do something like and this would be a triple consisting of a character, a boolean, and a string. Okay. So the constructor is this thing, the parentheses with the comma. So given an A and a B, you get a pair of an A and a B. So there's only one constructor. And because there's only one constructor, typically a function operating on pairs will also only have one defining equation. So for booleans and for maybes, our previous examples, we always had 2 equations. I mean, if we did the pattern match, I mean, if we had like 2 maybe arguments, it was maybe 4 equations. But I mean, for each, if you do a pattern match on a boolean, you get the true case and the false case. If you do a pattern match on a maybe, you get the just case and the nothing case. But if you do a pattern match on a pair, you only have one case, because there's only one constructor. So for example, 2 functions also that you find in the prelude extract the first or the second component from a pair. So they are called first and second, or first and sind. And you could define them yourselves like this. So only one equation for each, so the only possible constructor. So given a pair, an A and a B, what's the first component? Well, it's A. And what's the second component? It's B. So if I apply that to my, here, this example, so first of this pair is the Q, and second of this pair is the true. There are no equivalent nice predefined functions for triples or quadruples or so on. But for pairs, we have first and second. Another simple example on pairs would be to swap the components. So take a pair of an A and a B and turn it into a pair of a B and an A. And again, we would only have one defining equation because there's only one constructor. So given the A and the B, well, we just swap them. So I could try this for my example here. Okay, that seems to not to be built in. Fine, then I define it. It's probably somewhere, but in the standard libraries, but not in the prelude. So let's define it. So swap goes from A comma B, B comma A. And it does the obvious thing. And this, incidentally, is a good example of how the type system helps you to, I mean, where there's no possible way to, I mean, there's only one way I can write this function. Because I have these two types, A and B, and I don't know anything about those types. So there's no way for me, I mean, I don't know what they are. So if I have to produce, here on the right-hand side, a pair of a B and an A, I need to produce a B and an A. And I don't know anything about the types, so the only thing I can possibly do is take the A and the B that I already have on the left-hand side. So this is the only possible implementation of a function with this type. So in this case, the type of the function completely determines the implementation. I mean, this is like not so common, but it's relatively common that you have very few choices. And in this case, if I use these holds, and basically ask the compiler for help, then it tells me, I mean, it suggests the possible fill somewhere, I suppose.
Yeah.
For that, sorry, I have to close.
Relevant bindings.
Yes, yes.
More to the top. There.
Yeah, but that's the binding. So I know I have something of B and A, but it also suggests how I could fill the hole. And basically the only suggestion is the B and loop, but loop would be an error. So if I don't want to produce an error, basically the only choice I have is to use the B. Yes?
Could you kindly repeat from the beginning of the swap?
From the beginning of the...
Re-implement swap, if you can explain what it does.
What it does? It swaps the two. I mean, you have a pair of an A and a B, and it turns it into a pair of a B and an A. So it just swaps the order of the two things. So if you have a character and a Boolean, then it turns it into a Boolean and the character. So it just swaps the order of the two. And I'm just saying that this is an example. If I give you this type signature and ask it to implement it, I don't have to tell you what it's supposed to do, because there's only one way to implement this, except if you use something like undefined. But if you want a total function that for each, I mean, for all input pairs produces an output pair and doesn't crash, then the only possible implementation is this one. Because I need a B and an A. I don't know anything about the types A and B. So the only thing I can possibly do is use the ones I already have.
If we know that B was int, for example, we could just ignore the B and put like a 3. And we can define almost
Yes.
infinite options. In this case, because we have no idea what B and A are, we have no other chance than just split them.
Yes?
Can you create a function, maybe, let's say reverse pair, which maybe when someone is given maybe 4 elements of a set and it runs inverse, and it should also be possible, maybe somebody might put 4 elements but 3 elements, and it also reverses it. And like, I was afraid to implement such a thing where it's bringing an error.
What is the signature of the function you want to write?
It's reverse pair, then A, B, C, D, a set. Then now it just reverses B, C, D, A. It works if I put 4 elements, but I don't want it to work also when I put 3 elements on it.
But, okay, so let's first write it. And where do you now put 3 elements? What do you mean with 3 elements?
Okay, if maybe you run your function for maybe, let's say 1, 2, 3, 4, it runs for 3 to 1. But when I put 1, 2, 3, it does not bring back 3 to 1.
Right. Yeah. Because you have to provide 4 values. Like, because in the type, the only match is a tuple with 4 values. So if you write 3, there's no match for that value. So it's basically like if you were passing a different type altogether.
So if you wanted to achieve the same thing, I'll also have to define a
You
function
have
for
to create a tree. There's ways to avoid that, but you should have to create like a 3 and then a 2 and then a 1. So you should have, yeah.
Yeah, because I mean, this function, you are saying this function takes a quadruple. And if you give it a triple, then you just provide the function with a value of the wrong type, and then it just complains. So you can't, I mean, it expects 4, so you must give it 4. If you don't, then it won't work.
Yeah. So there's a bunch of those functions already defined up until like 20 values in the prelude. But also there's this thing that we didn't cover yet, but I explained before, the currying, that allows you to provide not all the values right now. It won't crash, but it won't return the final value. You can just select, partially apply everything, and once you are ready, you have the value that you need, the final one, you can give it.
Right. And there are like more advanced ways like template Haskell to write these types of functions automatically.
No, like the last lesson.
Right. More questions?
You said the one way to avoid having to implement each instance of the tuple
Yeah.
is choose Cardano. Yeah, so Cardano something out there is like one type, right?
Mm-hmm.
Yeah.
So but Cardano is like when you have a type and you want a type, you don't like let's say a function which takes two types and produces one type, right? When you carry is you provide just one type and then you produce another function that takes
Yeah.
one type.
Mm-hmm.
But then in tuples, one tuple is one type.
Yeah.
So how do you kind of avoid?
Yeah.
How do you
Each value is a different input. So can you like split the tuple into several inputs?